It is sort of based around the ERC Synergy grant that we got jointly with Maxim Kontsevich and Bertrand Inart and Marcus Marinho and myself. Just want to tell you that on our webpage, and you find it simply by Googling ReNewQuantum, you can find a way to, where it's described on the front page, how you sign up for announcements for this seminar. So you're welcome to disseminate that to people, whoever might be interested. And then during the talk, we ask that everybody mutes their mic. And if they want to ask a question, please unmute and ask Maxim a question. And then else we will take questions afterwards, but it's okay to ask questions during the presentation also. So with this, I would like to give the word to Maxim Kontsevich to give the first talk. The title is Exponential Integrals, Lefschetz Thimbles, and Linear Recursion. So please, Maxim.
Okay, so I start to share screen. Just a second.
Yeah.
Take some time. Okay. Just wait a second. Oops. No, it doesn't want to. Yeah, okay. Okay, so you see my first page, yeah. Okay, so so I will talk about subject of resurgence, but in a very kind of simple baby case called linear resurgence. When resurgence will be, you'll see essentially tautological, but it's very rich mathematics still behind. So I will speak about exponential integrals and why what's called Borel summation, how to make sum of divergent series, works for them. So we start with a complex manifold. It will be not necessarily algebraic manifold, as you'll see, of certain dimension n. At some moment it will be infinite. Then we have a holomorphic function on manifold, also just a map from manifold to complex numbers, analytic map. Then we have a holomorphic volume form, mu. In local coordinates, it's just some density times dx1, dxn. And we get some cycle of which we want to integrate, and cycle will be non-compact. And it will go to infinity in such a way that real part of my function will go to plus infinity. Okay, and then for any small number h bar, positive number, but very small, if you kind of cross finger assume that everything will be fine, there will be some convergence, we can write an integral depending on h bar. We integrate over cycle, exponent minus my function divided by h bar multiplied by density. So in local coordinates is f of x divided by blah, blah, blah. And we want to study its asymptotic expansion as h bar goes to 0. H bar is a Planck constant. And just first example, one can try to think it's imagine like x will be a fine line. Then cycle will be real numbers. Function will be x to the power 4 plus x. Sometimes if she goes to plus infinity, the both sense of real line. And a density will be dx, and we have this integral exponent minus whatever h bar this polynomial times dx. So it's a typical example of integral which you want to study, and it's asymptotic expansion. So this function of h bar will be not analytic h bar equal to 0, but it will have something like Taylor expansion. Okay, so how we can calculate such an integral? So first of all, in this integral, if we want to push our cycle as much as possible to the right, in the sense that we project by function to a complex plane, then it will stay in the rightmost possible half plane, right half plane. So we define, so we consider domain when real part of my function is bigger than some number rho, and try to see whether we can push my cycle in this domain. And we try to find maximal possible rho when it's still possible, when we can still realize cycle in this domain. And definitely it should be critical values, because if it's not critical, then topology doesn't change. We can push further. But if it's a critical value of real part of the function, then it's critical value of
sorry, Maxim, just to interrupt a second. So the participant list is sort of blocking part of your screen. So if you could remove that participant list. Yeah,
okay,
great.
okay.
Thank you.
It's strange because no, do I share screen or do I share on
Yeah,
the PDF file?
So far, it's working fine.
No. The question: can you see the small icons on the left or not?
No, we don't see icons on the left, but we see your mouse fine.
Okay, that's okay, fine.
Yeah.
Okay, good. It's a bit strange. Yeah. What goes on? Yeah, if you have critical point of a real part of holomorphic functions, that's critical point of holomorphic functions as well. So this raw critical will be a real part of some complex critical value. In fact, it could happen that simultaneously it's real part of several complex critical values, but I'll assume for simplicity that it's just only one appears. The more general case, it's completely similar. Yeah, so what happens in this case? So we have just one critical values with whose real part is raw critical, and maybe there are some others with another critical real part, and we can push my cycle near this critical value in such a way that it will project to a little orange interval which goes to the right. And what will happen? We'll have the projection of my cycle will lie in the union of a small orange interval and a half plane which lies still further to the right. And all of this orange interval, my cycle is a kind of fibration. It's a family of n-1 dimensional cycles staying in the fiber. And these cycles, when this distance between critical point and my point on a orange interval goes to 0, then it's this limit will be 0 in homology group, so it's called vanishing cycle. Yeah, so we see that we represent as a family of kind of vanishing cycles, which collapse to 0 cycle, and something which is exponentially small. Okay. Okay, now how we can calculate this interval? Just again, return to this picture. We have family of, we have this exponential small part, which we ignore in the moment. And here we have a family of, one parameter family of cycles and fibers. So we first integrate along fibers, and then integrate along this orange path. So what will be, what we integrate? So consider function of small real parameter t, which is volume of n-1 dimensional cycle with respect to natural density. It's a quotient of n dimensional density with BDF on a level set of my function. And so kind of we say that this n-dimensional integral, it's we have this overall factor, critical value, and then we have integral over exponent minus t o h bar of some function of all t, and we get this. Finally, we get exponential bound on the rest. Yeah. So what is this function of all t? The claim it's essentially analytic functions, modulus for small details. So this is a theorem which follows from Hironaka's resolution of singularities in analytic setting at not algebraic geometry. It doesn't matter. So this function, all t, is the sum of absolutely convergent series. So it's like analytic functions, like an analytic function, but the small difference that exponents are not integer numbers, could be rational numbers, but with a common denominator, and they are all strictly bigger than -1, so it will have positive number -1, and also logarithms could appear, and logarithms appear up to some bounded power. So in algebraic geometry, it's called quasi-unipotent monodromy. So unipotent responsible for the powers of logarithm, and quasi it's for roots of 1, which appears as denominators. Okay, so I get a convergent series of this form, and the rest we ignore. And now we can integrate. You can just cut for large t and ignore the rest. And you see the whole thing has the following expansion. So we take exponent minus critical value divided by h bar, and again certain series of the same nature. Again, will be rational powers now without -1 and powers of logarithms. But coefficients will be slightly different. You just integrate term by term. So let's assume, just to simplify life, there's no logarithm. In what I will explain today will be no logarithms. So this powers of logarithm will be 0. So my expansion is series in rational powers of t. And now I claim that this normalized by value of critical value integral. It has a scientific expansion where C lambda are the following guys. You have your coefficients A lambda of original series and multiply by values of gamma function. Why you do it? Because if you integrate individual summand, t to power lambda 1 minus 1 times this exponent, you get exactly, by definition, value of gamma function multiplied by powers of h bar. But now you multiply things which is convergent series, so to grow like exponentially by factorials, and series is definitely divergent. So only asymptotic expansion. So you don't really have clean way how to get value of this sum. And those old trick in mathematical physics, kind of 19th century mathematics, how to get numerical value for such divergent series. It's kind of formal procedure. You have divergent series, sum of C lambda h bar to power lambda. Now you divide, and coefficients grow like factorials. Now you divide each coefficient by value of a gamma function. So to get the convergence 6, multiply, change variables instead of Planck constant, put like variable t. So it really imitates our consideration kind of backwards. We reconstruct volume function from this asymptotic expansion, get exactly coefficient say lambda. And now what happens with this volume? The volume you can extend analytically essentially along any path, unless you meet some singularity. But there are only countably many singularities, and if you draw your path at random, so you'll have no problem. So just draw kind of generic path goes to plus infinity to ensure the convergence. And now the summation method is the following: how to define regularized value of this guy. You make this Borel transform extend along the path and integrate exponent minus t of h bar. And again, you hope for the best that the integral is convergent, and that gives you the value of this divergent series. Now, so that's a simple method. And so let's compare to our original question, what's going on, why it works. So when we choose a path, we can shift it, those paths starting from 0 in kind of, because it's abstract formulation, which doesn't know about any critical values. But we shift it to static its critical value, and so we get a path on the domain of my function, where the function maps. And this path is generic. We can lift our family of vanishing cycles along this path up to infinity. So we get something similar to what we have before. We get some n-dimensional integration cycle, which goes to plus infinity, which is different from my cycle somewhere in strictly on the right of my critical value. And what can happen? So if on the right of the critical there is no other critical values at all, then we're essentially done, because this difference between these two cycles lies very on the right, and we can push it further and further to infinity since this integral is 0. It's like usually, like in complex analysis, you prove that some integrals are 0. You push the cycle of integration to the main where function is goes to very fast to 0. Yeah, so you see that this Borel summation gives you exactly the value. Otherwise, you can maybe choose a wrong contour, but the contour will differ by something which is strictly on the right, and then you can repeat the procedure, and you represent your original integral, maybe sum, maybe infinite sum of kind of Borel summed path for larger critical values. Yeah, I think it's maybe if anybody has any question, you can ask them now. Hello?
Mm-hmm.
Yeah, okay, so it's clear. I just continue.
Mm-hmm.
Yeah, so it's a very simple story. So why Borel summation works for these exponential integrals, and essentially you do not think more about Borel summation anymore. This talk. So I'll try to make some again assumption to make life simpler. That all critical points are isolated and non-degenerate, so Morse and holomorphic sense. The second derivative of my function is, if you calculate in local coordinates, you get non-degenerate quadratic form. And so it means that the function can be locally represented as constant plus sum of squares of coordinate. And also I assume that all critical values are pairwise distinct. Okay. Then what goes on? Because when I have this Morse critical point, holomorphic Morse critical points, near each critical point I get essentially a unique vanishing cycle, which is diffeomorphic to a sphere. Because in the complex coordinates, I can change coordinates, so my function will be sum of squares of holomorphic coordinates, and if I put real coordinates, I get equations for the sphere. Okay, now what is the Lefschetz thimble? So for each Morse critical point, and for any generic direction, some direction will be bad. So direction is specified by an angle up to 2 pi. The Lefschetz thimble is a subvariety, which is kind of cycle of integration, diffeomorphic to Rn. It's non-compact. And how it's obtained? We take a vanishing cycle near my point and extend along the straight path in direction theta. So from each critical point, we draw straight ray in direction theta and lift our integration cycle. It's kind of unique up to homotopy. So we get a n-dimensional cycle of which we can integrate our function. So it's ill-defined if my ray meets another critical point, but otherwise it's okay. So when we have this Lefschetz thimble, we can, it's kind of very specific canonical choice of integration cycle. Then we can use it in the following way. So we take now h bar as a complex number. Before h bar was a real number, but now the main game here to complexify Planck constant. So take complex number and take direction theta to be argument of the h bar. So the integral will be again kind of real fast decaying along the Lefschetz thimble. And we integrate over Lefschetz thimble my function, so to be very, very fast decaying. Then there is a leading term because we start with some critical value, just cancel this critical value, this normalization. And also I divide by thing which usually appear when consider Gaussian integral 2 pi h bar to power n over 2. And n is dimension. It's just for convenience. And what happens, it's a part of general story, but it's completely trivial here, that this series has a divergence asymptotic expansion. Now all exponents will be integer numbers, 0, 1, 2, 3, exactly because when I put this prefactor, which comes from Gaussian integral. So I get a certain form power series expansion, which is divergent, and with the claim that coefficients you can calculate kind of formally using form power series. It doesn't really depend on direction of your Lefschetz thimble, because as I said that for some directions wrong, not defined, and so the function is kind of discontinuous. But asymptotic expansion is the same. Okay. So this. So we get a lot of this normalized function, and each normalized function is defined and analytic outside of several rays. When on this ray we meet another critical values. Yeah, so it's a function on complex plane when I make several cuts, but actually on each sector it extends a little bit across the cut. So if you make analytic continuation, this will be some overlap. Now, I will describe now this what's called jump formula, how this normalized integrals change if I cross Stokes some kind of bad direction. So I choose some direction, and suppose we have oriented line with this direction theta in C, such on this line at least 2, maybe 3, 4 critical values, and I kind of label them in increasing order, first, second, up to K. And then if I rotate a little bit my angle theta and start to draw, kind of rotate H bar, then I emanate a little bit different kind of red and green rays. And they're completely okay. So it means that if I just move a little bit, I have well-defined normalized function. And I can see the limits of this function and at my bad direction. Limits I denote by plus and minus, go from minus side to plus side. And I get a collection of a whole vector of values of my integrals on the plus side, collection of vectors on my minus side. And I claim that one can calculate, let's say, plus side through minus side by applying certain metrics. And metrics has a very, very special form. First of all, the last integral will not change because it will not, the ray will not meet any other critical values. It's the last one. And so on. So it will be upper triangular matrix with one on the diagonal. And off diagonal terms will be of very special forms, will be integer numbers multiplied by exponents of difference between critical values divided by H bar. So these numbers are called Stokes indices. And you can calculate it in the following very clean fashion. Namely, you have two, just in the right low corner, you have two say, points, alpha and beta, the alpha and the beta, on this Stokes ray, on the line parallel to Stokes ray. The beta is after. Now you make this slightly rotated red thimble emanated from the A, but from the B you emanate green thimble in kind of direction opposite to what I have on the upper picture. So I get two things, two non-compact cycles which intersect properly in some, if you kind of generically intersect finitely many points, and this number is this intersection number of two cycles. Now, so you can calculate pretty easily this integer. Yeah, so that's a simple formula. It just in topology compare cycles, what's going on. And so we see from our exponential integral, we have the following thing. We have collection of critical values and collection of integers associated to any two different critical values. And all this jump formula can be formulated in the following way. Let's consider trivial vector bundle with fiber over complex plane, H bar, with fiber with kind of basis labeled by my critical values. But now, if I have the Stokes ray, where something bad happens, I just make a cut and change two copies along the ray using this form, this matrix S theta, which was on the previous picture, which is pretty explicit matrix, and we get a section of a new holomorphic bundle. So what is called Riemann-Hilbert problem in such situation is to try and to find some to understand why it's a holomorphic bundle, to find some base of holomorphic section or holomorphic realization of the glued bundle. So in a kind of classical terms, we should find matrix valued function outside of Stokes ray, which is called G, which satisfies the jump equation on the cuts. It's exactly the same equation which I have before. Before I have equations for vectors, but now just equation for matrices, the same equation. And with the boundary condition that this matrix goes to identity matrix when approach 0 along any sector. Yeah, so that's a question which doesn't know anything about my function, just using this Z alpha and N alpha betas, this data. And there are some ways to solve it. And effectively, I think we should develop some effective computer program to do it. So it's some separate mathematical problem. Suppose we solve it. Now, what happens? We consider we have this my vector of normalized integrals, which is function outside of a vector valued function outside of race, divided by my matrix function G, we get another function J. And because I cancel this this G and I satisfies the same rule, this ratio has trivial jump. So so it means that it's a holomorphic function in H bar. And how we calculate its Taylor expansion? The Taylor expansion is product of Taylor expansion of G and I, vector I. For G, we have this some special machine, and we can calculate theoretically its asymptotic expansion. It's divergent. For I, we also can calculate expansion. It's kind of calculation is form power series of my functions. We integrate. In other divergent guys, we multiply, get convergent thing. And now, how we can reconstruct this function I? Of course, I is just J times G times J. J we can calculate because we can calculate its Taylor series. It's convergent. We put it in the computer, gets actual number. And function and matrix valued function we know from our whatever method for Riemann-Hilbert program, and we get this number I. Yeah, so it's you see that it's kind of completely different strategy to Borel summation. We don't make any integration of a path at all. So we kind of play with some form power series and some Riemann-Hilbert program, and miraculously solve these things in another different way. Yeah. So
may I ask you a clarifying question? So this I normalized. It's an analog of the inverse to Borel transform. It's an integral of a symbol.
Yeah, it's integral over symbol. Yeah, it's exactly
in resurgence, this Borel transform was kind of infinitely. It can be continued.
It's not Borel transform. It's actually expansion of integral. I normal is expansion of the integral.
No. I mean that there are two things. There is one way.
I don't know Borel transform here at all.
Yeah, that's why I'm asking this question before you go to examples. Yeah. So it's about the relation of this way to get analytic function, which is J. The only analytic thing here is J. And in the conventional resurgence, the only analytic thing was infinitely continued Borel transform.
It's a volume. Yeah, it's a different story. Yeah.
Yeah. So that's just. It's a different story, and
it's a different story, but gives the same number because in this exponential integrals, it's another way to get the same number.
Mm-hmm. Yeah. Okay.
So that's Here we just one little remark. When we make gluing, we make kind of on arrays we get matrices depending on parameter. We get linear maps. And in more complicated problems like WKB expansion, one get non-linear gluing, and it's what's really theory of resurgence about. So this a linear example is kind of baby case of resurgence. Yeah. So now,
Maxim, could I ask a question also? So I think on slide 5, you gave a formula for this regularized value.
Yes.
This is so J is another way to give a formula.
It's completely it's a different way to get the same number.
Yeah, but it's this thing that J gives you.
Yes, exactly.
Yeah. Okay. Thank you.
Yeah. So now we'll go to classical kind of 19th century mathematics. The second part of 19th century. There are plenty of special functions, and they have interesting asymptotic expansions. In some points they are analytic, but in some points they are bad, and the question is how to calculate them effectively. So I'll start with kind of area function in optics. from my perspective, my variety is complex numbers. Function is x cubed over 3 minus x, and density is dx. Now we can calculate immediately what are critical points. It's plus minus 1, take derivative, solve equation, get x plus minus 1. Then calculate what are critical values. It's a minus 2/3 and plus 2/3. And kind of sneakily on the left draw these two critical values just to see here on the screen, z1 and z2. z1 is on the left on z2. It's very easy to calculate here what are stock indices. You get from 1 to 2 it will be plus 1, and 2 to 1 will be minus 1. Okay, and how all this jumps works in this basic example. Let's start with I2 normalized, not I1, by I2. For I2 normalized, it's kind of nice thing because you can go to the right without any trouble. Yeah, there's no eigenvalues on the right, and in fact, this function extends for all C. I2 normalized is defined for all C outside except negative numbers, because if you go to negative direction, you hit z1. So you get function on this cut, and this function is given by the formula in terms of area function. Area function is this integral cosine whatever t cube, almost the same integral, but it's one should kind of see you have rescale variables, and you see this formula. So this area function, sum of power, it's area function is the entire function, but you apply to minus 2/3 power of h bar and multiply exponent by h bar, and this thing has asymptotic expansion, and this is double factorial, so it's actually goes like 3n factorial divided by 2n factorial, so it goes like n factorial. So you see it has n factorial growth, and function on the another cut, you just reverse variable to minus I and multiply by square root of minus 1. And what are jumps? Now, for example, consider z1, and now it has now the cut is positive real numbers, and you consider how to jump from plus part to minus part. You get plus 1 times this exponential factor multiplied by I2 normalize, and conversely for I2 normalize another jump. So you see these numbers plus and minus 1 and exponential factors, which is exactly this parts of the Stokes matrices. Yeah, so it's very, very simple example. And all classical functions, if you look on kind of huge, like Grashstein and Rizhik, whatever volumes of special functions, you have hundreds of pages of like Bessel functions, and there are 4 types of Bessel functions: K, J, IH, K, blah, blah, blah. Probably engineers knew it better than mathematicians. And the most simple one, it's for my purposes, will be modified Bessel function of second kind with index 0, K0. So what is going on? My variety is now C star. I remove 0, function is x plus 1 over x, measure it's dx over x. Again, critical points are plus minus 1, critical values minus 2 plus 2. So it have the same, up to scales have the same picture, have just 2, one on the left, one on the right. But stock indices are slightly different, plus 2 and minus 2 instead of plus 1 and minus 1. And then you get Bessel integral, and if you have this normalizing factor and asymptotic series, which was calculated by Hankel. Yeah, so it's a very similar story, and you go R function, whatever, all classical special functions, and when you get interesting asymptotic expansions, goes to the whole story. Okay, maybe I'll stop now. If there are any questions?
So I guess that.
Sorry?
Yeah, I just want to ask a question, Maxim, John here. So I guess that all of these coefficients in this expansion sort of are recursively determined by these jump formulae. Is that right?
No, coefficients asymptotic expansion. No.
No.
No. They're not. One can have different functions with the same jump formula, but different asymptotic expansion. You take some. Yeah, the simplest thing, you multiply by 2, whatever. You see that this jump formula do not depend on measure mu at all. And integral depends on measure mu.
Yeah. Okay.
Yeah. This is kind of more often for me.
Does that correspond to sort of changing the trivialization of the bond? Yeah. Okay, that's what I was sort of asking. I see.
Okay.
Yeah. Okay.
Yeah. So now we go to more serious example when we have infinitely many critical values. It's still classical mathematics. So let's start slowly. So we have C star, and on C star consider some one form, this strange one form, 1 minus 1 over x dx. It's not a differential function because form has non-trivial period, 2 pi I. I go around the circle. So in order to see that it's a differential function, we should go to the universal cover. Exponential cover, just go by exponential map. So the cover coordinate on the cover denoted by t. So x is equal to exponent of t. And then we can see the pullback of my form, which is dx minus dx over x. It's dx minus dt. It's easy to write what is differential of its function is exponent of t minus t. Okay. Now we have this function on this universal cover C. It has infinitely many critical points. Calculate what's the derivative is exponent of t equal 1, 2 pi I times integer. And critical values is 1 minus 2 pi I times integer. Again, sneakily on the right, I draw my critical values in some scale. Yeah, so that's, now they go vertically in both directions. And what is normalized integral? First, I claim this normalized integral doesn't depend on which critical point on the cover you choose, because you normalized. You in the cover you have for different critical values with different values, but one differs by another by constant. We remove in the definition of normalized integral. So we can calculate for k equal to 0 this normalized integral. So we get this integral. This is normalizing factor and then integral. So I repeat normalizing factor, and I go to coordinate x back. So I see this integral, and again up to rescaling I see gamma function, gamma integral. And I get plenty of factors here, which exactly factors which you see in Stirling formula in asymptotic expansion of factorial. Yeah. So it works for on the right plane, and on the left plane it's kind of a bit similar to what we have before. I recall actually for every function get minus things in negative. Here it's 1 over things as positive values, and again doesn't depend on index. And this guy has asymptotic expansion. It's Stirling formula. These are not Bernoulli numbers. Bernoulli numbers appear when you take logarithms. Now, so get this classical situation. So what really goes on? For this regularized integrals, we get essentially two functions because the choice of kind of representative critical value doesn't matter. So we have what? We have one function on the left half plane, one on the right half plane. Right half plane, what I draw this very nice expression Gauss function, and the left half plane it's 1 over this guy in the opposite point. And what are jump formulas? So jump formulas are very easy. So there are these two functions both extend a little bit to vertical ray and to negative ray, and formulas are different on different rays. So we have one formula, another formula, and you see that you get IL is IR minus exponent times IR, and here you get similar stuff, but here it's -1, so you get arithmetic progression, and it gives you formula for Stokes indices. If you translate back to integrals labeled by integers, these integers which you get, it's -1. You get some infinite matrix with -1, some upper diagonal and parallel to main diagonal, and +1s in the everywhere on the lower diagonal. So
may I ask you a short question? Is this the same as a number of gradient lines for the function on the universal cover?
It would be, but it's maybe I go to one of previous slides. You see that on the right corner, I draw when several critical values stay in a line. Yeah, if you consider gradient lines go from ZA1 to ZAK, A3, it happens. It's bumps before to previous critical value. Yeah? So it's kind of not really well defined thing.
Only okay. Only
yeah, if two, but in our case they are aligned, and the better way it's to shift a little bit Lefschetz thimbles that drawn in the corner. Yeah, that's the correct definition, not how many critical gradient lines go from one to another, but intersection number of slightly tilted Lefschetz thimbles. Yeah, so we get this table of stock synthesis. And there is a little puzzle which I think it's easy, but I kind of a bit, I don't know how to say what's going on at the moment. The story is the following. If H bar is inverse to non-zero integer number, kind of plus minus 1, plus minus 2, and so on, then this function descends to C star valued function on C star. Because periods of my function will be proportional to 2 pi I, and if I divide by integer, 1 over integer, I multiply by integer, so ambiguity will be absent. So I get C star valued function on C star for the special value of R, and here I can make contour integral. It's again immediate to calculate these things, but the question is how to relate to integrals over Lefschetz thimbles, and it's not immediate because you go to universal cover, you multiply it by infinity. So there is a little puzzle to solve here, and similar question actually appears in many other stories in quantum channel series. We will see it later. Okay, now go to even more wild situation when I have infinite dimensional integral. Integral calculating heat kernel, Brownian motion. So let's start with a real analytic Riemannian manifold, which has some kind of reasonable, I don't know exact criteria, complexification. So what I'll start now, it will be more and more examples, but no general theory. Yeah, so we have our real analytic manifold with a nice metric in a sense, and we have 2 points, and consider path integral, some infinite dimensional integral, depending on positive Planck constant. We consider parameterized path map from 0, 1 to my manifold, so connecting my 2 points, and we integrate exponent minus s of phi d phi. So I get certain functions called Dirichlet functional. I integrate like kinetic energy, half of speed, square of speed, calculate in terms of metric. Yeah, and defy it's some kind of fictitious object. We can try to think that all paths in Riemannian manifold form again infinite dimensional Riemannian manifold, and because it's Riemannian, infinite dimensional manifold should have some kind of Lebesgue measure. Now that's how we can try to see it, and how to relate it to our picture. So we have this domain of integration, and it's some infinite dimensional manifold, which can see infinite dimensional contour in some complex manifold, which is space of path connected points in complexification of my manifold, MC. And this, because my metric extends to some holomorphic expression, this S of phi extends to some holomorphic function. And Lebesgue measure, okay, with cross fingers, it says expressed to some holomorphic volume form on infinite dimensional manifold. Yeah, so it's not rigorous at all, and the only thing which can say rigorously is called Feynman-Katz formula. This we say that this integral is defined as actually value of heat kernel. So we make a Brownian motion, random walk on my manifold, walk time t, and time t we identify with a Planck constant, and calculate the density of probabilities that we start at P0 and end of P1. And kind of in physics notation, we take exponent minus half Laplacian, multiply by t or h bar, and take it will be integral operator, considers density at points p0 and p1. So if yeah, so it's like in Euclidean space we get Gaussian. So this we can consider the definition. And we just can in h bar goes to 0, it means in terms of, because we interpret now as a time, it will be short time asymptotic expansion of heat kernel. And here's this kind of story about large deviations. So the claim that if you have two faraway points and time is very small, the main contribution goes from kind of straight path from p0 p1, and the asymptotic will be the following: it will be 2 pi t minus dimension of manifold O2, exponent of will be things which decay very fast exponentially. This exponent minus distance divided by t, and time certain asymptotic series.
Yeah, so when you say resurgence, you mean Borel transform, you use it. Yeah.
Yes. So the conjecture is that, yeah, first the sequence has factorial growth. Yeah, that's I think is known. Yeah, people in differential geometry studied a lot this expansion. But my conjecture is that in nice situations, this series will be not only factorial growth, it will be resurgent, and Borel transform will have singularities at certain numbers which you can guess a priori. It will be critical values of my function f, which will be squares of length of geodesics connected by p0 p1 divided by 2. And what is complex geodesics? We just map 0, 1 to my complex manifold, again with boundary conditions. Satisfying formally Euler Lagrange equations will be, and calculate what is action function and get these numbers. Now, so this things was so this kind of my preferred example is hyperbolic plane, or you could go hyperbolic space and dimension, or sphere. Surprisingly, this heat kernel in a form which kind of really good for me was calculated pretty recently, 50 years ago. So the heat kernel is given by the following formula. You get some prefactor, and then you integrate. And look on this integral. L is the distance between my 2 points in a hyperbolic plane. I get exponent minus 0 t. It's exactly what I need in my game, yeah, times dz. And divide something below. And what I claim it's square root of polynomial of infinite degree. I consider hyperbolic cosine of square root 2z. Hyperbolic cosine is even function. So you can apply to 2z, you get entire function. It's well defined. Entire function is a polynomial of infinite order. And I remove a constant, I get some polynomial of infinite order, and I get kind of like hyperelliptic integral, except of this exponential factor. So I speak about hyperelliptic curve of infinite genus. That's my variety here. And one can see what are critical values. It's exactly when this thing vanishes. Hyperbolic cosine equal to z equals cosine L. And you get very nice picture, you get some integer points on parabola in a complex plane, infinitely many of them. Yeah, and that's all very nice. Yeah, so you get essentially the same what we have by general theory, but there is some little bizarre factor which I highlighted by yellow, exponent minus t over 8, and kind of for a long time I thought, what does it mean, this factor? What is the role of this factor? But in fact, it's very easy. In this Feynman-Kotz formula, we said that we multiply x1 over half Laplacian. Maybe it's not Laplacian, but Laplacian plus constant. Because, and I think that's this 1 over 8, it's the right choice of constant from hyperbolic plane. I thought first that it's maybe it's what's called scalar curvature, but it's not. It's something different. If consider hyperbolic space of dimension n, it's scalar curvature something like n minus n times n minus 1, and this is n minus 1 square. Yeah, so it's slightly different from scalar curvature, and it's really interesting to understand how to what is right heuristic and what what is the meaning of Feynman integral in terms of hit kernel precisely.
Is it a linear resurgence question where the Riemann?
It's linear, of course. Yeah, you take integral, divide by some density. That's it. Yeah, and also this a little bit wrong far of t, but that one can also think about because space of paths is infinite dimensional, and we divide by dimension, so we have zeta regularization. So something goes with how we interpret dimension in this case. But yeah, kind of dangerous factors is exponent t over 8, which can be understood that we have changed kind of rules for Feynman-Katz formula. And it works more or less this kind of small corrections for other kind of homogeneous spaces, like compact surface arithmetic. You have it's called Seilberg trace formula and so on.
I have an elementary question.
Yeah.
So this T is H bar here.
Yes, T is H bar. Yeah.
And the previous Feynman-Katz formula, where is the H bar in the explicit?
No, I wrote, this just on this page, I wrote T equal to H bar.
Okay.
Okay. Now I go to kind of last part. It will be 3 examples at once. And hypothetical is essentially they look at 3 series of examples. It should be just one example, one series of examples. And it's related to different equations in geometry in dimensions 3, 1, and 0. So the 3-dimensional class of examples is the following. What will be variety x3? It will be some infinite dimensional. It will be z car of some another variety, like in gamma function integral. And what is other variety? X3 prime, it's connection on some bundle on 3-dimensional manifold with complex semi-simple group up to gauge equivalence. And X3 will be universal cover, the fundamental group of the 60 prime is Z. Okay, what is one-dimensional situation? Again, it will be cover of some x1 prime. X1 prime, it's easy to describe. I have a certain torus of dimension 2n, complex torus dimension 2n, and I get 2 Lagrangian submanifolds, which are not only Lagrangian, they are algebraic, defined actually over rational numbers, and what's called K2 Lagrangian. I will explain later. What is it? K2 Lagrangian? Yeah, so the formal definition, if you know what is K theory, maybe field of rational functions, the sum of these guys should be equal to 0. And my manifold is C infinity path, which connects these 2 Lagrangian manifolds. And this guy has certain Z cover. It's not obvious, but it has some certain Z cover. Okay, and the third situation is the following. It's kind of 0-dimensional point of view of physics or finite dimensional mathematics. And we consider, again, smaller variety, it's the following guy. We consider torus, not even dimensional, but arbitrary finite dimensional torus, maybe 1-dimensional, and remove certain toric hypersurfaces, then product over some powers of my variables is equal to 1, like hyperbolas or diagonal, whatever. So you get remove finitely many such hypersurfaces. Then this thing has certain abelian cover, which will be not algebraic, and this on the top, this cover again have Z cover. It will be x0. Yeah, so we'll explain step by step what are functions of these varieties. Now, so we start with 3-dimensional situation. So this variety, or maybe x3 is connections up to some certain choice, some covering. The functional is Chern-Simons action. Yeah, if we have, let's say, a connection with in trivial bundle for group SLN, it's given by matrix with coefficients in one form and trace is 0 is one form. And the functional is given by this integral, so this reform which you integrate. But if you apply the gauge transformation, the function will jump by some integer power of 2 pi I square. Not 2 pi I, but now 2 pi I square. And now, like for gamma function case, there are special values of 2 pi LK. It also could be -1, -2, and so on. We get a well-defined function on this z quotient, and we get a kind of compact cycle of integration which consists of unitary connections, and that's what physicists call quantum Chern-Simons theory at level K. Yeah, so it's really integral on this quotient by z, not by on this universal cover function exists. Okay, second story, it's about drawing paths between two Lagrangian subvarieties. So what are examples? Okay, I don't want to explain what is K-theory, I just give you basic examples which are sufficient for all purposes, suppose. So we have two-dimensional complex torus and put a holomorphic algebraic symplectic form, this kind of standard form. And as kind of typical standard example of K2 Lagrange variety is given the following. If you have conjugate coordinates zi and zn plus I for certain I, then zn plus I is equal to 1. So just, or you can choose for each I, 1 minus zi. Make a choice for each I, which equation you write. Yeah, so you get. Sorry, somebody is. Sorry, somebody is asking some question. Or? I don't hear.
Daniel, could you maybe mute your computer?
Oh, okay.
I'm going to do it for him. I think he's on the phone. Okay.
Oh, okay, yeah.
Yeah.
Okay, yeah. Okay, yeah. So I get this bunch of what's called K2 Lagrange subvariety, or you can apply group SP2 in Z acting by monomial transformation in Z, or linear transformation logarithms. So there are plenty of this K2 Lagrange subvariety, and what actually goes on if you have K2 Lagrange subvariety and consider any two-dimensional chain with boundary on the subvariety and make integrals of this to form, then get integer multiple of 2 pi r square. That's more or less should be another analytical characterization of what a K2 Lagrangian subvariety. And now I will not say precisely what the value of function, but I will on space of paths connecting to R, I'll say what is different between values of two different paths. So I define function up to a constant. If you have two paths connected L0, L1, and just connect endpoints of this path, both of some paths on L0 and L1, and filled by foregone. And integrate of this foregone homomorphic symplectic form omega. It will be, by definition, difference of values. Okay. Now I go to last case about dialogarithms. And so what we need to make the story, we have a finite subset of non-zero integer vectors in a lattice. And for each element, we have some non-zero integer weight. And then we also have an even quadratic form with integer coefficients, so given by symmetric matrix with even entries on diagonal. And from this, we can construct a multi-valued function. We take, first recall there is a dialogarithm function. It's multi-valued function represented 0 and 1, near 0 to given sum of convergent series, scale square. So it has many, many branches. And we take multi-valued function, we take linear combination of dialogarithms of monomials with weights, and some bilinear form and logarithms. Yeah, so get this function. It's multi-valued. It has countably many branches, but its differential is defined on some ZM cover of exactly what I told you, torus minus some branch of hypersurfaces. Because when you write was differential of function, you expand in d log of xi, and coefficients will be certain integer combinations of logarithms. And it's very nice because for integer combination of logarithms, it's logarithm of some expression is defined up to 2 pi I, integer power of 2 pi I. So you choose for each this linear combination the value of the whole sum, and here you get one defined function, well-defined one form. So you get well-defined one form on the ZM cover, which depends on all this data. And then it's easy to prove that periods of this form proportional to pi I square. And to get, again, one well-defined function, go to another Z cover. Yeah, so get this cover of cover. Okay, what goes on? And all you have questions: three-dimensional geometry, one-dimensional geometry, or kind of zero-dimensional physics. And each set, this critical values, is a finite union of arithmetic progression with a step 2 pi s square, which is pretty kind of minus almost 40. It's actually important that it's so large number. When you do numerics, it starts to hurt. So the picture of critical values is kind of some kind of finite picture repeated with this shift 40 infinitely many times. So we have some kind of we surround by this some group denote. So we can label critical values by some finite things belongs to this domain alpha underlined and some integer to which we add this shift. Why the picture is like this? Because in every situation, if you look what is going on, what are critical points, you have to hold some system of algebraic equations with rational coefficients. And typically, systems kind of maximally determined has dimension 0 space of solutions. Sometimes not. But this more singularity correspond to dimension 0. So in case of three-dimensional manifold, these critical points are flat connections, or the same as representation of fundamental group. And any reductive semi-simple group can be a Chevalier group defined over rational numbers, and fundamental group has some generities and relations, so you solve huge system of algebraic equations for matrices. So that's your algebraic variety. In case one, this is subvariety side defined over rational numbers and intersect them. They have all middle dimension. Intersection should be zero-dimensional. And in case 0, what you solve is that derivative is 0, and exponent of logarithmic derivative is algebraic expression. So you solve system of actually M equation on M variables. Yeah, so and what I claim that whatever you do, this three-dimensional one or zero-dimensional geometry, you get the same critical values. They belong to certain very nice countable subgroup, countably generated subgroup of C mod 2 pi I z squared. It's called image of Borel, Williamson-Borel regulator for K3 indecomposable. So this K3 indecomposable Q-bar, it's huge space, roughly have the size of purely imaginary algebraic numbers. Okay, and now this is my last slide. Kind of one big conjecture is that when you do like Chern-Simons theory, this K2 Lagrangians or linear conventional dialogues, you get essentially the same story. And when you match them, you match not only this finite collection of arithmetic progressions, but also the Stokes indices. And Stokes indices is some integer number associated to two critical values, but because you have shifts, it depends only on difference. So you get underlying indices running through this finite set, and difference is some integer number. And why so optimistic? Because yeah, first it's not random that critical values coincide. Maybe the whole topology should coincide. But also what we see in the case of heat kernel, we get infinite dimensional path integral, and indices are the same as for certain finite dimensional exponential integral for some infinite genus hyperelliptic curve, for example. Yeah, but now the case when you get linear conventional dialogues, it's really kind of honest mathematics, and one can easily study the topology of the things. For example, I just write some ad hoc example with no particular reasons, because from my perspective, all examples have the same value. I just take dilogarithm plus square of logarithm, the simplest possible example. When I write this variety, x0 prime, I should extract logarithm of certain expression. So it will get x squared of 1 minus x is equal to exponent of t. I get this z cover. Or you can write x equal to I hope I solved my quadratic equation right. And what I see, I have square root of something. Exponent of t is, of course, entire function, but you see it's a polynomial of infinite degree. So I get infinite genus hyperelliptic curve. It's exactly the same story as in this path integral. And actually, I expect that maybe path integral will fit to this dialograming examples as well. So what's going on? We have just a case of one variable is already interesting. So we get a map, exponent of f divided over 2 pi I from this variety to C star. It's complete parallel story with a gamma function example. And this map is ramified to finite set of points in C star, which will be correspond to this arithmetic progression. In monodrome, it's completely accessible. One can really calculate it. Let me say by word what is a monodrome. So you get on C star, you get for example, in this one-dimensional example, you get countable fibers, but the monodrome around each critical values will be just permutation of 2 points. Very simple. And then there is also monodrome around 0, which is essentially one semi-infinite, kind of two-sided infinite cycle, like shifting integers. And so it should specify which point you permute. And I think it's kind of also manageable in high dimensions. Before I was afraid of infinite dimensional variation of kind of this constructible shift, but this is a really kind of fine algebraic situation and described in finitely many words. So one can calculate everything. And the trouble here, we get infinitely many Stokes rays. And if you consider Stokes rays, if you go just to the previous picture, you see that if you connect these 2 points, you can go rays which are very, very closer to horizontal directions. Oops, sorry. So the Stokes rays form a kind of infinite picture. You get many directions, which is two accumulations, to accumulation point to positive real ray and negative real ray. So you get infinitely many Stokes matrices, which are pretty simple one. But when you have this many cuts, you can just have many transformations. Just try compose all of them. It's familiar in wall crossing formulas. This infinite composition, and you can replace infinitely many cuts by one cut, and it will be you get Riemann-Hilbert problems with just 2 cuts because positive in negative direction, but with more complicated function which you put here. And what is angle ordered product of infinitely many Stokes matrices? It's essentially monodrome of Q difference equation. What I claim it belongs to mere world of kind of algebraic Q difference equations. Eventually, to this Q substitute this value and get the whole story. Yeah, so it's very new kind of development, and I don't have any numerical examples yet, but presumably it will explain many mysteries in like a quantum knot theory and so on. Thank you.
Okay, so thank you very much for the talk, Maxim. So now let's go to questions.
Okay.
People have some questions.
Yeah, I do have some questions. So first, I did not understand your argument in favor of the conjecture, because I look for complexified Chern-Simons. Of course, it's infinite dimensional, but you somehow can indeed single out finite dimensional piece and something quadratic in the direction.
No, it's a general story for any kind of reasonable path integral. You have kind of
but it's exactly what I am saying. It's a general exactly in this sense. What is special here?
No. What I claim is the following: in this infinite dimensional space or complexified space, when we draw this infinite dimensional Lefschetz thimbles, I claim that intersection numbers of Lefschetz thimbles are the same as intersection of Lefschetz thimbles in some finite dimensional situation.
But what is the finite dimensional situation?
No, it's a certain linear combination of dialogues and squares of logs.
No. Why?
Why?
You just claim that 310 are equivalent. So
yes. The first thing.
The question is why?
Because critical values coincide. It's the
okay,
first.
so it's not a big deal, you know.
No, it's a big deal. Two numbers coincide. It's a big deal. We have uncountably many numbers and coincide.
All right, but the question is why this n alpha case coincide in different stories. That's
it's a conjecture, but no, I am optimistic because we have two functions with the same set of critical values.
All right, so it's just based on your general optimism. Okay.
General optimism, of course, like in mathematics.
Yeah. Okay. May I also ask you 1, 0? You said that it's from physics. It's 1 and 0 dimensional. What kind of physics do you mean?
It's not physics. Physics in 0 dimensions, finite dimensional mathematics.
Yes, but why it's 1 dimensional and not
why?
2
Because
dimensional?
Consider path it's made from
okay.
It's functional dimension.
Okay. And how the parameters match? Again, for this conjecture, in one story you have some reductive group. It's your parameter. You have some weights.
No, one should. You see that. There are many ways to do it. For example, if you consider like Lefschetz invariance for 3-dimensional manifold, you can first divide your manifold by simplices, then write some explicit formula, some indices running from simplices, and consider formally what are critical points. You get critical points of some linear combination of logarithms squares of logarithms. So it's kind of it's not unique. Like when you try to calculate Chern-Simons invariance, you should decompose your manifold to some elementary pieces. You can do it many different ways. So different things can give the same answer.
Okay, and can you, since you are on this slide, can you just remind why Borel regulators appear in Chern-Simons story? Is it a conceptual answer?
Yes, because you have your manifold. If you have a representative fundamental group, your manifold maps to the classifying space of group as a discrete group.
Yes.
And you get so you get a class homology of a group as a discrete
group. Okay, yes, thank you. Now I recall now. So see, it's still morning here. So okay, good. Thank you.
Okay.
So maybe I can add one thing to your discussion there. So Maxim, if you could go to the last slide again.
Okay.
So I can add a bit of optimism. So if you consider the 3 manifolds that are search-free on the figure 8 knot, then William Mistegard, who's also here, my former PhD student, and I, we have been able to prove that there is a way to map 3 to 0 in that case, so that your conjecture works.
For this Stokes synthesis,
Yes. So for search-free in the figure 8 knot, we now know the whole story. It's quite complicated with sort of analytic estimates of rewriting. Taking the Resurgence formula, rewriting it into an integral using the residue formula involving tans and cotans, and then Fedayev's quantum dialog. And then we analyze the asymptotic expansion of that. And we eventually end up with exactly a problem of the type 0 that you wrote. And it has exactly the Chern-Simons values corresponding to flat connections. And Stokes indices should.
No, there's really no reasons not to believe
And one could imagine taking, the general definition of the Resurgence invariant and then using quantum dialogues same way to re-express R matrices, and then, do all the finite sums again via residue formulae. And then one will have to do some complicated estimates on the analysis to understand that you have the right asymptotic expansion when you replace quantum dialogues by dialogues. But in principle, I see that there could be a possibility to address 3 to 0 this way in general, but I think it would be hard.
And still, since you kind of recalled some other works, this N alpha K indices, they are just those, they are really a number of gradient lines. in this Witten story.
Yeah, we don't know that in our approach, but in
but
general,
then should solve kind of Kapustin-Witten equations for dimensions. It's pretty complicated.
Maxim, we can hardly hear you. Could you put your mic a little closer to your mouth?
Okay.
Yeah, so then basically you are saying that instead of solving this complicated Kapustin-Witten equations, you can just do very, very finite dimensional.
Yes, especially curve. It will be, even computer can do just continuation of curves, make intersections.
Yeah, provided the conjecture is true. Yes, that's okay. Yeah.
Yeah. So, are there any more questions?
Yeah, I do have a question. It's
okay. Go ahead.
Yeah, it's quite simple. It's about slide 8. Maybe you already answered. So if you could please go back to slide 8. It's just a silly question about about the fact that you're saying that the Stokes indices are given by the intersection numbers of thimbles. Could you give me an intuitive reasoning behind that?
Because you see that if you can see the green, green rays going to the right and green rays goes to the left, this is a kind of dual basis. The intersection number will be diagonal matrix 1, 1, 1, 1, 1, 1 on diagonal and 0 outside, the identity matrix. So it will be dual basis, and that's why it's true.
Yes, but just I don't understand why the Stokes indices are.
No. You see that this Lefschetz thimble, red Lefschetz thimble should be linear combination of green Lefschetz thimbles. Certain linear combination. We don't know which one, and we consider this Lefschetz thimble goes into opposite direction, and it specifies us the coefficients.
Okay, I see. Thank you.
Yeah. Any more questions?
I have a question about your heat kernel expansion. I believe it was on slide 14.
Okay.
So right. So I suppose the left-hand side somehow involves the spectrum of the Laplacian. And
yes, of course, there is Laplacian here as well, but I don't speak.
And your expansion, the coefficients are somehow related to the length.
No, it's not exactly. It's because I don't call it trace of heat kernel. Of course, one can expand in eigenvalues. True. Yeah.
So I'm wondering whether you can use your formalism somehow to get a Seiberg trace formula out of this.
Yes. Essentially, what this says.
Sense also in the non-hyperbolic case.
No, the problem is that I don't really believe that this conjecture about resurgence is true in a kind of very large generality, like for C-infinity metrics or even for real analytic metrics. It should be very, very special metrics, kind of.
Thanks.
Yeah. More questions?
Okay.
Maybe not. So maybe we thank Maxim for his nice talk. So thank you very much. So people are making clapping hands.
Okay.
So I can just say that we have another lecture planned for the end of July, which should be Bertrand Inard, and then Marcus Marinho will speak in the end of August, and maybe I will speak myself in the end of September. And then we're going to have some more talks scheduled from there on. So yeah, stay tuned. We'll send out information. And you're welcome to spread the news about this seminar. So thank you very much, everybody. So bye-bye for now.